Traditional pharmacology operates on a core mechanical assumption. The higher the concentration of an active compound, the stronger the response from the target cell. We expect a linear relationship, where flooding a biological system with a massive dose guarantees a pronounced, immediate physiological spike. However, adaptogens like Ganoderma lucidum, Reishi, entirely defy this linear pharmacokinetic model. Reishi functions through hormesis, a biphasic biological response where low-dose exposure triggers adaptation and balance, while high-dose exposure results in diminishing returns. On the left, a linear dose response climbs indefinitely. On the right, a biphasic hormetic curve reaches an optimal peak, then plummets. Consistent microdosing sustains the system at this peak, achieving long-term homeostasis. Conversely, a megadose forces a steep slide into acute shock. This overload triggers defensive protocols like receptor desensitization, metabolic waste accumulation, and immune overstimulation. Applying standard acute pharmacological logic to a hormetic system creates a biological mismatch. When the dose ignores the system's capacity, the compound's potential is lost to metabolic friction. To see why these limits exist, we have to look at the physical architecture of the human gut and liver. Our gastrointestinal and hepatic systems have finite capacities for absorbing and processing complex compounds. This grid maps the bioavailability limits for Reishi's two primary bioactive classes, beta-glucans and triterpenoids. We will trace how these compounds attempt to clear two primary hurdles, absorption in the gut and metabolic clearance in the liver, across both microdoses and megadoses. Efficacy is dictated by these rigid physiological bottlenecks. Exceeding absorption limits yields no systemic benefit. Beta-glucans are nonlinear macromolecules that interface directly with the immune system. They enter the body through the gut-associated lymphoid tissue, or GALT, specifically targeting the Peyer's patches. In a microdose scenario, small clusters of beta-glucans pass smoothly through the Peyer's patches tissue barrier into the lymphatic system. Once inside, they locate immune cells like macrophages, locking into dectin-1 receptors on the membrane. This creates a steady, sustainable stimulation of macrophage phagocytosis. The cell remains energized without having to alter its structure to handle the signal. This stability is contingent on a manageable supply. Flooding these receptors creates a different cellular outcome. This continuous, low-level nudge builds baseline immune readiness without triggering inflammatory exhaustion. When a megadose of these macromolecules hits the intestinal transport pathway, it creates an immediate biochemical traffic jam. If a massive flood of beta-glucans reaches the macrophage, the cell reacts to the overload by retracting its dectin-1 receptors inward. This downregulation prevents overstimulation. With receptors internalized, macromolecules have nothing to bind to, halting signaling. The excess polysaccharides that cannot be absorbed are left trapped in the gut lumen. This triggers an osmotic shift, drawing water into the intestinal tract and causing acute gastrointestinal distress, gas, and loose stool. Brute forcing the immune receptors leads to a localized toxic response and the suppression of the very immune activity the dose was intended to support. We see a similar bottleneck when tracking Reishi's lipophilic triterpenoids, specifically ganoderic acids, as they process through the liver. These compounds are systemic modulators, providing a mild inhibition of histamine release and supporting the neuroendocrine system. Because they are lipophilic, microdoses of these acids easily cross cellular membranes to enter the hepatic portal vein. In manageable quantities, these molecules navigate past resting liver enzymes, entering the systemic bloodstream. Under a megadose, the clearance load becomes overwhelming. The liver responds with an aggressive swarm of enzymes that attack and dismantle the triterpenes on site. The excess molecules are broken down before they can ever reach systemic tissues. Exceeding these hepatic limits does not provide more neuroendocrine support. It simply results in metabolic waste. Beyond the kinetics of a single dose, we must consider the physiological results of consistent exposure over weeks. The objective of adaptogenic immunomodulation is functional valence, not maximizing immune activity to 100%. Daily microdosing provides a continuous epigenetic signal that primes T cells and natural killer cells to respond accurately to threats without inducing exhaustion. This steady processing also recalibrates the nervous system by influencing the hypothalamic-Pituitary-Adrenal, or HPA axis. The HPA axis governs the transition between sympathetic fight-or-flight states and restorative GABAergic rest and digest pathways. Consistent triterpene exposure gradually dampens sympathetic overdrive. Over several weeks, the chaotic, high-frequency electrical signals smooth out into a slower, rhythmic wave. This smoothed wave eventually locks in as the new default baseline for the HPA axis, favoring a state of parasympathetic dominance. Profound stress resilience requires these gradual baseline adaptations, a shift that acute pharmacological intervention is structurally incapable of producing. Think of the HPA axis feedback loop as a highly complex, tension-based instrument. Microdosing is like the microcalibration of a tuning peg, a fractional daily adjustment that maintains perfect receptor sensitivity and system pitch. A megadose is the equivalent of striking that peg with a hammer, which can instantly snap the structural connection. These kinetic realities dictate how we must approach the chemistry of cultivation and extraction. To achieve a precise microdose, it is necessary to use high-potency, dual-extracted isolates that are standardized for specific ganureric acids. This precision contrasts with the common practice of consuming unstandardized ground fungal biomass. Consuming the massive volumes of raw fungal biomass required to reach specific bioactive thresholds introduces a secondary risk, the accumulation of heavy metals, often sequestered within unrefined material. In adaptogenic pharmacology, raw volume eventually meets a physiological bottleneck. Cellular precision and consistent dosing remain the only ways to achieve long-term homeostasis.